Just a quick intro. I'm Reid Mello. I work on the Globus team, and specifically Globus Compute, and we use Parsl heavily, sort of under the hood for Globus Compute. So I'm also a Parsl contributor. And I'll just talk about a new implementation that I've been working on to protect HTEX communication, which is the HighThroughputExecutor, with CurveZMQ. All right. Oops. So I'll just quickly go through the previous state of Parsl security, really as of, I guess, like before this morning or yesterday when we pushed the new release of Parsl, which includes the feature that I'm going to discuss. So we use ZeroMQ for HTEX communication. That's generally a high performance asynchronous messaging library. So I won't go into all the details about why we use ZeroMQ or what else it brings. We also don't even fully utilize all of the routing capabilities that come with ZeroMQ, but generally gives us some scalability benefits for, related to message queuing, having multiple connections to a single socket, some retry logic, etc. But this gives us unencrypted communication channels. So we basically just have open sockets on a number of our processes within sort of internal processes within the HTEX. There's also no authentication, so that means any process can connect to interchange or worker pools. Again, this is all sort of within your network. So Parsl you have to deploy Parsl in a secure environment for these reasons. Otherwise, anything on the internet would be able to connect into your interchange or worker pools. Here's a high-level diagram that shows some of the components within the HTEX. So we have these generally signify different processes. We have the executor, an interchange, and manager. I won't go into detail on what each one of these components do, but for anyone who's familiar, so the executor will send tasks to the interchange, which then makes its way to the manager. The manager in this case is like a worker manager. You can think of this as like being deployed on every node. The worker manager then will spawn workers, and for this we use the multiprocessing module. So there's no and the interprocess communication uses multiprocessing queues, so we don't need to worry about encryption here. So really the relevant channels here is between the executor, interchange, and then the managers. And each one of these blue dots signifies a ZMQ socket, and I should say an unprotected ZMQ socket. Okay, so just quickly go over what CurveZMQ is. So basically, it's an authentication and encryption protocol for ZeroMQ, and it's really the only officially supported protocol for ZeroMQ with encryption. There's ways to add encryption to ZMQ without using Curve, but this is the sort of de facto way to do so. It uses elliptic curve cryptography, which I won't go into a ton of detail about that, but basically, two kind of important characteristics is it uses short keys, so it has good performance. CurveZMQ closely follows Curve's CP handshake. So for anyone who's familiar with that, but the kind of relevant factors there are that it gives perfect forward secrecy. So we store long-term permanent keys, but then we exchange short-term session keys, and we destroy the session keys when the connection is closed. We also protect the client identity by never sending the permanent public key for the client in clear text. And by permanent here, I'm using the typical verbiage when discussing this, but really for our case, permanent actually means per run, because we generate new quote permanent keys and store them in the run directory for each run. So I'll get into the actual implementation of CurveZMQ on our side. So like I said, we generate new certificates for each run. We use shared server and client certs because all of the relevant processes that I mentioned before there's a shared file system, so there's really no need to generate separate client certs or well, definitely not a separate server cert. And we store all of these in the certificates directory, which is stored within the run directory. So again, this is on a per run basis, and this is a private directory as well. The executor and managers serve as CurveZMQ clients. So they're primarily responsible for verifying the server using the server's per run public key, which is sort of shared ahead of time. And the interchange is a CurveZMQ server, which verifies the clients using the client's per run public keys. And we have a dedicated thread that just does that on the server side, because obviously there's lots of clients connecting to the server. So here's kind of the updated high-level diagram of HTEX communication with CurveZMQ. So main things to note here is that, again, the executor and the managers are clients, the interchange is a server, the changing color here just signifies that these are encrypted sockets now. So kind of down here, protected ZMQ sockets. And then again, we don't touch these spawning of actual workers from the worker manager because we're using the multiprocessing module here. All right, so to enable HTEX encryption, it's very simple. You just set the encrypted initialization argument to true. So I just have a basic example here, and this is just, again, along with all of the other initialization arguments, you just set encrypted to true. By default, we have that set to false for reasons I'll get into in a minute. Well, actually, it's this slide right here. So there's some known performance issues depending on how you install the dependencies. So at a high level, CurveZMQ depends on libZMQ and libsodium. These are the main like underlying libraries that it depends on. And when you normally install PyZMQ, it'll also install these dependencies as pre-built binaries. And on many systems, I don't think this is on every system, but on all the systems that we've tested internally within our team, installing from PyPy can result in pretty significant throughput degradation. So anywhere from, actually, we've seen less than this, but just to be sort of cautious here, I'm saying 5x to 20x, depending on the payload size and a number of other factors. So there's a few different solutions that we know of to avoid this. First of all, install via Conda. So if you just do Conda install from Conda Forge PyZMQ, or if you install Parsl via Conda, you shouldn't have this issue, at least from all our testing. This seems to be a stable workaround. You can also install libsodium and libzmq separately. You can build from source, or I've tested on a number of systems using apt. So yeah, you can install those separately and then build PyZMQ from source, which you can do in a few different ways, but this is a simple way to do it. So you can just pip install Parsl so that you're getting the proper PyZMQ version that's required with Parsl, and just use the no binary flag for PyZMQ. And that's going to build the wheel locally without pulling down those pre-built binaries. And then you'll automatically link to your system's libsodium and libzmq. Okay, so I'll go through a quick code example just for anyone who's interested in what this looks like sort of actually within Parsl in the implementation. So for example, if you, I should say I built a CurveZMQ module within Parsl, so we can import this from Parsl, create client and server certs. So this is what happens at the executor when you start a new run. We instantiate client and server context. So this is very similar to, if anyone's familiar with PyZMQ, you create context within, you do ZMQ context, and then you use that to then create sockets that are associated with that context. And you can set, default options for the context, et cetera. So this works the same way. We just have to specify whether it's specifically a client or server, because that changes the types of options and things that we need to add to each socket. So then, yeah, you create sockets, same as you would with ZMQ context. And again, the necessary certs and options will be added to these sockets when they return. And then I'm just showing an example connection that can be established. And then we, can send some data. So that's the general kind of flow on how we're, at a high level, how the code looks between the different, objects in Parsl. Okay, I just have a link to the docs here, and I'll take any questions anyone has.
Is it performance degradation only with the encrypted ZMQ, or
yes.
Okay, so unencrypted still unaffected. That's great.
Yeah, I should have clarified that. Yes, so that's why we by default have encryption off, because we just didn't want, depending on how you install the dependencies, like we didn't want people to suddenly have and by performance degradation, I'm referring to throughput. There's always going to be some performance degradation when you add encryption, but it shouldn't be anywhere near what we would see, depending, depending on the installation. So
Mhm.
yeah, this would be, you'd have to explicitly go in, set encrypted to true, and then you can test on your own system and see if installing from PyPy is sufficient. If not, I also have these notes in the docs as well on
Mhm.
recommended paths to install from Conda or from source.
Excellent.
Do you have any numbers on the performance difference between the Conda installed HighZMQ versus the pip3 no binary flag installed?
I mean, I know I have some numbers from some of the testing that we had done previously, but
Yeah.
I don't off the top of my head. I mean, it looked from memory, it was about the same. Because
Okay.
basic,
Yeah, that's just what I
so
wanted to like just confirm.
yeah, because honestly,
Cool.
what led us to that, like sort of the troubleshooting path, was I know that you had installed with Conda and you found no performance degradation. I'm like, huh, that's interesting. So then I sort of just studied like how the Conda Forge
Mhm.
recipe
Yeah.
is doing things, and they're building everything from source, et cetera. So yeah, there's still some questions exactly why the pre-built binaries um, lead to such performance degradation. Like I can't actually pinpoint the exact reason, but you can sort of chalk it up to, if you're not building things on your local system, you're not taking, there's a number of things that if you're pre-building things on a system that's different than yours, yeah, exactly. Just any hardware acceleration that's relevant to your system. But it's still weird because with Conda, obviously you're pulling a binary as well, but I guess they're just building on more variations. So, anyways,
I believe Kevin said hardware acceleration in the comments.
yeah. Yeah, that's what I was just reading there. But yeah, that's exactly what I'm getting at. Just the differences in different systems. So when you're building from source locally, you're gonna take advantage of any special hardware that you have. And if you're doing a pre-built binary that's meant to just generally work on all systems, then you're not going to take advantage of the different processors you might have, et cetera.